Hi, I'm Helena McHugh. In this presentation, I will be talking about the history of coronavirus, how it infects one's body, how one's body combats it, and then potential vaccines. Since this past summer, I've been working in a lab studying immunology and the immune responses to SARS-CoV-2. So what is COVID-19? Just to get down the terminology, COVID-19 stands for Coronavirus Disease 2019. 2019 for the year it was first detected. COVID-19 is a part of the family of coronaviruses, which are called that because of the crown-like spikes on their surfaces, and corona is Latin for crown. The coronavirus family has actually been around for a long time, but coronaviruses are mostly circulating among animals, such as bats. It is really when a mutation of this virus arises in an animal, and a stable form of it is then passed down to humans, that we see an emergence of a new and threatening disease. In 2003, this was SARS, Severe Acute Respiratory Syndrome, and in 2012, this was MERS, Middle East Respiratory Syndrome. However, even though they had higher fatality rates, these were not as contagious as the current virus, SARS-CoV-2, and therefore did not lead to pandemics. COVID-19 is caused by the SARS-CoV-2 pathogen, which stands for the Severe Acute Respiratory Syndrome Coronavirus 2. So there are three lines of defense when a pathogen comes into contact with one's body. The first are the barrier defenses, which block the entry of many pathogens into the body. These barrier defenses are skin, hair, and mucous membranes lining the digestive, respiratory, urinary, and reproductive tracts. There are also innate immunity defenses and adaptive immune ones, which I will be touching on later. Once SARS-CoV-2 viral particles are ingested or breathed in, they enter the body through the lung epithelial cells, which are a layer of tissue lining the outer and inner surfaces of the respiratory tract. These cells promote gas exchange and have cilia, which help clear the airways. The lung epithelial cells have a weaker defense against pathogens than skin epithelia, which have a thick layer of protective keratin. The surface of the lung epithelial cells is coated with ACE2 receptors. SARS-CoV-2 binds to this receptor, which is how the virus starts infecting one's body. So when a pathogen first enters the body, breaking through the initial barriers of defense, the organism's immune system must be able to identify it as a foreign substance. Immune cells produce receptor molecules that bind specifically to molecules from foreign cells or viruses and activate defense responses. The initial innate immunity detection occurs minutes to hours after infection, while the adaptive immune response takes 4 to 7 days to respond to the pathogen. Innate immunity is a non-specific response to a virus or bacteria, which means that regardless of the type of virus, one's body will have the same innate immune response. Therefore, the variety of cells that are involved in one's innate immune response are not recognizing a specific molecule on a particular pathogen, whereas adaptive immunity is. So adaptive immunity occurs with tremendous specificity and is enhanced by previous exposure to the infecting pathogen. The adaptive response relies on T cells and B cells, which are types of white blood cells called lymphocytes. T cells kill host cells, activate other immune cells, B cells, and produce cytokines. B cells fight bacteria and viruses by making Y-shaped proteins called antibodies. So how does this relate to COVID? The cells shown on the previous slide recognize coronavirus, triggering the release of cytokines, which are small molecules, small proteins important to cell signaling. This leads to the activation of the immune response. The typical immune response and symptoms responding to the SARS-CoV-2 pathogen are commonly seen as the ones listed above, and others may be more specific to the individual as a result of any underlying conditions. This graphic displays the variety of reactions to COVID-19. The research that I've been participating in has been to analyze and interpret the difference in immune responses in patients that develop severe and mild cases of COVID-19. So what causes patients to have a severe response to the virus? And also just to clarify, the severe response is what results in hospitalization. So patients can have this response for mainly two reasons: either an insufficient or excessive T-cell response to the virus. This means that either one's immune system is so strong and active that in its response to the virus it is actually attacking itself, or that one's immune system is not strong enough to protect one's body against the virus. An overactive immune response to COVID is referred to as a cytokine storm. Cytokines are proteins involved in one's innate immune reaction, and cytokine storms are when these proteins attack their own tissues rather than directly responding to the virus. As you can see, this image shows one's lungs. These cytokines attack the linings of the lungs and break through the surface, causing fluids to flow into the air sacs and making it very hard to breathe. This is what pneumonia is. Also, around this time of year in flu season, it is very important to get the flu vaccine because the flu and COVID affect the same types of cells. So if someone gets the flu and then COVID, their body will be weaker and they will have a much more severe reaction to the virus than they would have without the flu. This works the other way around too. So if you get COVID, then the flu, it will be much harder to fight and your cells and tissues will already have been damaged. Besides the severe and normal cases of COVID-19, patients can experience an asymptomatic immune response to the SARS-CoV-2 pathogen. Around 20% of infected patients are asymptomatic, which means they experience symptoms too mild to distinguish from their normal state or no symptoms at all. This feature of the coronavirus is one reason why it is highly contagious and threatening, especially since asymptomatic patients can still spread the virus. So why are some people asymptomatic? There is not a clear explanation for why some people have an asymptomatic response to COVID and others do not. For example, some people in their 70s have had a mild or no reaction to getting the virus, while some healthy people in their 20s have had a very severe response. This doesn't always make sense, and so there is some aspect of the immune response that is definitely unpredictable. But the prevailing reason for an asymptomatic response has to do with one's innate immune response to the virus. So why, for the most part, are children asymptomatic? Well, this is not completely known as well, but as children, they are constantly exposed to bacteria, and so they typically have very strong innate immune reactions. This means that they are much better able to clear a virus out of their system before it even triggers the adaptive immune response. However, if they have the virus, they are still able to transmit it to other people, regardless of whether they have symptoms to it. So there is some good news. There has been recently some very exciting news regarding the COVID-19 vaccines. Biopharmaceutical companies Pfizer and Moderna have released their phase 3 vaccine trial results, and Pfizer's vaccine was 90% effective, while Moderna's was 94.5% effective. They should be approved for distribution by the FDA within the next month. However, there is not enough for everyone, so priority will go to first-line healthcare workers, but the quantity will definitely pick up next year. So there is in fact some light at the end of the tunnel. If you have any questions, you can email me at hmchugh21@riverdale.edu. Thank you.